Hi all, in this video we're going to introduce some applications of exponential functions. We're actually going to, in general, introduce the exponential functions using applications. So you're going to see a little compare and contrast. We're not only going to be looking at exponential applications here, we're going to look at linear as well because there's some similarities into the way we set up equations and the bits and pieces of equations that tell us certain things about the graph. So the first one, we have a research experiment where we have a colony of 100 fruit flies and we determine that the colony triples every day. So these are just really simple ones to get us going and start to see how exponential equations look and how that relates to the graph and so on. So if we start the colony with 100 fruit flies. Let's go ahead and fill in the table. That means at 0 days, there are 100 fruit flies. The colony triples every day. So after 1 day, there are going to be 300. And just to make a little note of where that's coming from, we take the 100 that we had before and we triple it. After 2 days, there will be 900 fruit flies. And again, to note where that came from, we take the 100 that we started with and we multiply it by 3 2 times. If we then triple again on the 3rd day, we will have 2,700 fruit flies, which we get by taking the 100 and multiplying it by 3 times. And then on day 4, we'll triple again and we'll have 8,100 fruit flies, which we get by taking the 100 and multiplying it by 4 times. Okay, so the pattern that we should see in the table is that every time our input increases by 1, our output triples. This is an exponential pattern. So exponential patterns should always show repeated multiplication. If you increase your input by a fixed amount, you should have to multiply your output by a fixed amount. So here we're multiplying by 3 over and over and over again. Okay, so we can plot this and get a graph, and then we'll see if we can turn this pattern into an equation. So 0 days, this is 1,000. I'm going to say we're right around here, really low. 100 fruit flies, really low, at least relative to this scale. After 1 day, we're up to 300. That's a little bit more impressive, but not even halfway to the first grid line. 2 days, we're at 900. We've almost hit that first grid line. 3 days, we're at 2,700. 4 days, we're at 8,100. And if we connect the dots, you start to see an exponential shape. This is exponential growth. Okay, so when we see this shape get steeper and steeper and steeper, sort of reminiscent of an x squared, but the exponential functions always end up getting steeper than an x squared or an x cubed, a power function. So these exponential functions get really steep. They might start off slow, but eventually they always beat the power functions. Let's see, if we've got the graph, let's go ahead and look for the equation and see what it tells us about the graph a little bit as well. We have this pattern where in each of these, we are starting with 100 and then we're multiplying by 3 a certain number of times. And if you can see the connection here, when it's 1 day, we've multiplied by 3 once. When it's been 2 days, we've multiplied by 3 twice. When it's been 3 days, we've multiplied by 3 times, and so on. So what we're getting here, let's say that D is the number of days and F is the number of fruit flies. We're getting that the number of fruit flies is a function of the number of days, and it follows the rule that we start at 100 and we multiply by 3 once for every day that's passed, so D times. So again, when you see this repeated multiplication happening, multiply by 3, multiply by 3, multiply by 3, you're going to be building up powers of 3. Exponents represent repeated multiplication, which means an exponential function, one with the variable and the exponent, is going to be representing a situation where we're multiplying by the same value over and over and over and over again. So this model represents a population that starts at 100 fruit flies and triples every day. Yeah, I think that's all I have to say on that one. Okay, so let's look at another one, and then I will generalize a little bit for you. Okay, in this one, we have 100 milligrams of medication given intravenously. The amount remaining in the body will decrease by 10% every hour. So first we're going to fill in the table and look for the pattern, and then we'll do the same thing, see what the graph looks like and see what the equation looks like. 100 milligrams is the initial dose given, so that's going to be the amount of medication after 0 hours. After 1 hour, we're supposed to have that decrease by 10%, which means we will be down to 90 milligrams. And we got that by taking the 100 milligrams we started with and multiplying it by 0.9. If your first thought was to take 100 minus 0.1 times 100, so if you think of percent decrease as a subtraction, try to train yourself to think about it as a multiplication. That's how we build up these simple exponential patterns instead of much more complicated patterns that involve a multiplication and a subtraction. So if we start with 100% of something and it decreases by 10%, we're going to end up with 90% of what we started with, which is where the 0.9 is coming from. On the second day, we're going to decrease by 10% again. So we'll get 81, and that is our 100 now multiplied by 0.9 2 times. On the third day, let's see if I can keep track. I think so. We're going to be down to 72.9. And we got that by taking our 100 and multiplying it by 0.93 times. Okay, on our last day, I'm going to check this one. I'm not doing this one in my head anymore. If we take 0.9 times our 72.9, we get 65.61. And that was from taking the 100 and multiplying it by 0.9 4 times. So we're always referring back to this 100 that we started with and saying what we had to do to get here. And again, that's what builds up our exponential patterns. By multiplying by 0.9 over and over and over and over again, we build up this exponent. It was 1, then 2, then 3, then 4. And that's where the exponential function comes from. The thing that is varying is the exponent, which means the variable will be in the exponent, which means it's an exponential function. Okay, oh, I see that I have terribly wrong units here. Let me just adjust. So let's knock off a couple of zeros. We want to start at 100 milligrams and decrease. It looks like I just copied over the numbers from the previous graph. So let's say instead of 10,000, we've got 100, 80, 60, 40, and 20. After 0 hours, we have 100 milligrams. After 1 hour, it's down to 90. After 2 hours, it's at 81. After 3 hours, it's at 72.9. After 4 hours, it's at 65.61. Okay, so this one is deliberately kind of hard to see what's going on. If someone looked at this and didn't think carefully about it, I think it would be really tempting to say that this is a linear pattern, but it's not actually linear. There's a little bit of curve to it. Let me see if I can make it look that way. And then I'll show you more of the graph on the calculator so that you can see what's actually going on. It's not linear because linear, so this is exponential decay that we're seeing. Exponential growth if it's increasing, exponential decay if it's decreasing. If it was linear decay, you would see subtraction by the exact same amount over and over and over again. So if we decrease by 10 here, we'd also have to decrease by 10 here and here and here. And that's not quite what's happening. So let me just show you a little more of this picture. We had 100. Oh, and I guess I'm jumping ahead. So let's peek down here. We need an equation if we're going to check the graph on our calculator. So similar to the last one, I'm starting with 100 and I'm multiplying by 0.9 once for every day that passes. I'm sorry, once for every hour that passes. So if we say H is the number of hours and M is the amount of medication in milligrams, then M of H is 100 times 0.9 to the H. Again, you want to show that you started at 100, that you multiply by 0.9 for every hour. Okay, so back to my graph. Let me think about this. If X is representing the number of hours, I'm just going to go ahead and set my window. I know that on the y-axis, I want to see 0 to 100. And I know that on the x-axis, seeing 4 hours was not enough to really let me see the curve shape that was happening here. So let's go, I don't know, let's go 24 hours. See what happens over a full day. And we want our y's to go from 0 to 100. So we're going to see x's from 0 to 24 with tick marks every 1 unit. And y's from 0 to 100. Let's go ahead. You don't have to change this, but oops. Let's go ahead and make it tick marks every 10 units so we can actually see space between our tick marks. Okay, so now I think we're getting a much better picture of exponential decay. Exponential decay starts out decreasing somewhat rapidly, and then it levels off and levels off. So you're seeing asymptotic behavior over here. This has a horizontal asymptote at 0. No matter how many times you multiply by 0.9, you can shrink your y value, but it's not going to get to 0 or below. So this is the exponential decay shape, and what's happening in our picture is we've zoomed in just on this little tiny segment, and when you do that, it can trick you a little bit about the shape of things. In fact, this is a big thing we talk about in Calc 1. If you zoom in enough on any nice, smooth, curved shape, it's going to look like a straight line. So this is part of your job if you want to use your graphing calculator to check something, is to know enough about the shape to realize when you've seen what's actually going on. Okay, so just to say some general stuff to wrap up this intro video, for the applications of exponential functions, we can use this kind of basic shape. And we'll make even a little bit more modifications to this than just what A and B allow. But to get us started, if we're thinking about exponential models as having the form A times B to the x, B is the base of your exponential function, and it tells you the growth or decay rate. And A is your initial value. A is the y-coordinate of your y-intercept. So we will see in some of our examples what to do with the x value if we want to make something happen more or less often than once every hour or once every day or whatever our time units are. But kind of basic starting point is if you want your y-intercept, you would plug in 0. B to the 0 is 1, so you just get A. So this number will always give you a starting place on the y-axis. And then this number will tell you what to multiply or divide your y value for every increase in your x value. Okay, thanks for watching.